motivation, I'm going to talk about mean estimation, okay, and come up with an incremental algorithm that will finally find the mean, okay, and then show the parallel between this algorithm or this idea to estimate the mean to that of, estimating the value function or, yeah, things like that, okay. So imagine you have a random variable v as I've written there with mean mu and finite variance, okay. And suppose you are given n IID samples, and what's the best estimate? I hope everyone has done at least some course on ML. Does everyone recognize that estimator? What is it? What is that? That's really the sample mean. Is someone seeing this quantity for the first time today? Is anyone seeing this for the first time today? No? Yeah. So the point is, now given that you have Rn, is there a way I can write down if I get one more sample? So I got n samples. If I get n plus 1th sample, okay, what would be Rn plus 1, which is the sample mean from n plus 1 samples? Is 1 by n plus 1 summation Vi, right? As trivial as that. But I could write this as okay. I mean, as trivial as that. What is that thing inside the bracket? That was the previous sample mean. Okay. So I can write it as n by n plus 1 into Rn plus 1 by n plus 1 into Vn plus 1. Okay. Now this is the same as writing it as Rn plus 1 by n plus 1 Vn plus 1 minus Rn. So your next estimate, is going to make a small adjustments based on the new sample, okay, how far it went away from the previous estimate, okay, and then throw in this thing, okay. Now there's nothing sacrosanct. I mean, so the point is, you can fairly generalize this. You don't have to stick to something like 1 by n plus 1. You can put in a general thing called a step size or a learning rate. Okay, you can throw in a learning rate here, and this update rule would still converge to, I mean, how many of you have seen something like strong law of large numbers? How many of you have done a course in probability? At least some of you, okay. So the point is, if I have an update rule like this, when I keep getting samples, eventually where will Rn go as I keep on getting samples? Rn will converge to where? Mu. Rn will converge to mu. Now the point I want to make is Rn will converge to mu even if I take something which is not 1 by n plus 1 but something else which I call the step size. Okay. In ML community people call it the learning rate, but I like to stick to step size. Okay. So this update rule can be generalized as follows. So that governs the increment. The step size governs the increments. You are adjusting your estimate of the mean in an incremental fashion as you see more and more samples. You will very soon see the parallel to RL, but okay. If so those are the conditions that you want to satisfy. Obviously, if I take eta n as 1 by n plus 1, it clearly satisfies. Okay. If you have not seen this claim before, summation 1 by n is infinity, but summation 1 by n square is not, it's summable. It's not infinity, but you are not restricted to choose a step size like 1 by n, okay? There are many other options available. And any such step size will ensure that this Rn updated according to that boxed equation will converge to the mean, yeah? Okay. Is this clear? Clear to everyone, whatever I just claimed? Yeah? Is this clear? I'm not going to prove this. So all of this comes under the purview of something called stochastic approximation. Okay. So this business started in 1951. Okay. I'm going to write down the Robbins-Monroe algorithm. Okay. So in general, suppose you want to solve a equation like that. You are given a function, you are not given the function, but okay, so you want to find the zero of that function. Okay. Yeah. So you want to solve h of x is equal to 0, and what are you given? You are given a box, and if you pass an x, what you get is h of x plus w, and this is a 0 mean noise. The simplest example is w has normal 0. See, I'm just trying to generalize. So we previously you wanted to find the mean, okay? You wanted to find the mean, but now I'm going to make it more general. What I want to solve is h of x equals 0. But I have a box which will just output noisy measurements of that function. See, the point is you get just one number. Nobody tells you that you are given a number. Nobody splits it into two parts and gives it to you. You just get one number, which is the value of that function at that point that you asked for, corrupted by noise. Okay, corrupted by noise. Do you understand this? Do you understand the setting? Now you want to solve h of x equals 0, and you have a feedback model like this. This is what you get. In this case, what one could do is do an update like mean estimation. What you could do is you keep an fix x naught arbitrarily and do xn plus 1 equals, you are looking at an incremental update, xn plus a step size which is as before, and you do h of xn plus wn. This is the classic Robbins-Monroe algorithm from 1951. I think at least I owe a lot to Robbins. He started bandits, he started stochastic approximation, and I got a job. Yeah. Any questions? Now please understand, so the point is all the RL algorithms that I am going to present today are, this is the template for all of them. This is the template update. I can write TD algorithm where I write down, when I write down temporal difference learning algorithm, I just throw in a particular H. When I write down Q learning, I throw in some other H and things like that. So if you at the outset, if you don't understand this update rule, then you have to ask a question now, okay? All right? Of course, you need some conditions on H, like H is Lipschitz and all that. I'm not getting into the theory of that, okay? Now, okay, I'll just add that. H is Lipschitz. Okay, I'll write down the convergence claim at some point. But the point is, under reasonable conditions, xn can be shown to converge to x star, where x star satisfies h of x star equals 0. Okay, we'll write down that claim very soon, but I'm telling it orally. Yeah. Yeah. Is this update rule clear? Now I can take, now the point is the classic gradient descent algorithm is just a special case of this. What should I do for there? what would be the H there? If I want to optimize a function f using gradient descent, then H is just grad f. Okay, and what you see is noisy measurements of, you are given noisy measurements of the gradient. Okay, you are given noisy measurements of the gradient, and then you can do gradient descent, the stochastic version of it. But in RL, yesterday you must have seen this. When I want to find the optimal policy, what is the type of equation that I am solving? Is it like what kind of an equation is it? The Bellman equation. It's a fixed point equation. When I say fixed point equation, I'm solving roughly an equation like f of x equals x. Okay. So many RL recursions are like fixed point iterations. Okay. Value iteration is like trying to find a fixed point. Okay. So we will. So the point is, if I want to find the fixed point, okay, using this algorithm, what should I set h to? F of x minus x, that's all there is to it. If I set h to f of x minus x and run this update rule, then what I get is, it will converge to a point where f of x minus x equals 0, which is like saying that it will converge to the fixed point. Okay, got it? So that's really the idea. So the h is more general, as long as it's Lipschitz, which is a fairly, general assumption, this update rule converges. So I'm trying to spend a couple of minutes on this simply because later I'm just going to invoke this algorithm for different cases. And now if you don't get the main idea behind this algorithm, then yeah, it's like one of those movies where you miss the first scene and you lose it. Yeah. Any questions? Under some conditions, okay, I'll make those precise later. It can be shown that xn converges to x star with probability 1, okay, where okay, as I said, two special cases, okay. If we want to solve this problem, okay, imagine f is even convex, even otherwise, if it is smooth, it is okay. Oh, I'm so sleepy. Okay, in this case, what you get is gradient descent. In the first case, what you get is gradient descent. In the second case, what you get is a fixed point iteration. Okay, yeah, the learning variant of it. Is this clear? Clear to everyone? So I just take the update rule and set the h as I like, based on the problem at hand, and I would get, so most of this, so we're going to ignore this, but there are several algorithms that come under this framework even in the context of RL. All policy gradient algorithms do something like this. They parameterize the policy and try to find the best policy within that parameterized class. So that would be policy gradient. Again, I'm not talking about it. I'll focus on part 2 in this lecture. Okay, part 2, which is fixed point iteration, and that naturally carries over to temporal difference learning and Q learning. Got it? Is this clear? Where the best example is put H as steeple. I'm using R simply because I want to keep the, notation. I don't want to bring in the J's. So R is like the J, okay? You have n states and you want to estimate the cost at each state, okay? J of 1, J of 2 and so on. I've just put it as a n-dimensional vector R, okay? All right? And then what do you want to solve? You want to solve HR equals R, where H is your favorite Bellman operator or the other operator particular to a policy, okay? This is what you want to solve in an MDP context, all right? And so I'm going to put out this fixed point iteration in a more general context with not a scalar parameter, but a vector parameter and an operator, okay? And it's the same idea, so what I want to write is, now what we have seen yesterday is a direct method. What's the direct method? Start with R0 and keep on applying H. What was this yesterday? What method this turns out to be? This is value iteration, okay? But the important thing is what goes into that H or T is the transition probabilities. You're not given that in today's situation, okay? So we're going to bring in the learning angle soon. The other option is even in the, or you can do a smooth update. So you can do Rn plus 1 equals 1 minus eta n into Rn plus eta n into Hrn, okay? I mean, even in the MDP context, you can do something like this and it will still converge. It's almost like value iteration, okay? It's very much like value iteration, okay? With step sizes satisfying those conditions before. Okay, so you keep on applying H as before, but you're smoothing it out with the step size, okay? Now, the point is if I'm not able to see Hrn exactly, okay? But what I see is I see a noisy version of it, okay? If I pass an Rn, you want to find the best R, which is like solves Hr equals R, okay? That's the best R. Now, I have a box which will output for a given R, Hr plus some noise, okay? Now, in a RL setting, what you got is roughly, you pass a R and you get HR plus W, where W is a noise. We'll make conditions on noise precise, but imagine you see noisy versions of this, okay? Zero mean, okay? Zero mean noise, but you don't see HR, but you see HR plus W. Now, given this, what can I do to find, say, let me put it as R star, HR star equals R star, okay? I want to find R star, okay? Now, what can I do? This is all I got. I still want to do some incremental update like this. I want to do something incremental like this, but I don't have this. Instead, I have this. So what should I do? I just use this there, okay? Yeah? All right? So the algorithm will be Rn plus 1 equals 1 minus eta n Rn plus eta n into Hrn plus Wn. Now this is the template for most of the incremental RL algorithms, okay, which try to find a fixed point. Okay, you can take this algorithm update rule, and if you want to evaluate a policy, I can plug in a particular H and I get the temporal difference learning algorithm. And if you want to find the best policy, then I can take an update like this, I throw in a particular H and I get the Q learning algorithm. We'll get there very soon, okay? So is everyone clear about this update rule, right? Is everyone clear? So this is the build up. I mean, I started with mean estimation. I got to a point where, I can fairly generalize to find the zero of a function. And instead of finding a zero of a function, I can even find fixed point. And instead of sticking to scalar parameters and functions, I could generalize to a vector parameter and an operator. That's where we are, okay? Yeah, is this passage clear? Any questions? No questions? Is this clear? We'll just go on, okay? Now, under what assumptions can I ensure that Rn converges to the fixed point, okay? Yeah, and for that I'll just do a brief detour. But before that, what I want to say is, assuming H is well behaved, like the students here. Yeah, I just went to my daughter's school and people were screaming. And the instructor was asking, who is talking? I mean, everyone is talking. Like, who is talking? I mean, noise. Wn is 0 mean plus bounded variance. Okay, AS is almost surely, which is the same as with probability 1. Don't want to erase this now. Okay, now we need H to be well behaved, like the topper in a class, or those in the front benches, yeah, or those who give good TCF scores, yeah. And say classes are great, or the best teacher, need to get something like that, yeah. Not like you come on time. I don't know why people care about that. Does the instructor teach you well? Did you like the subject? Anyway, what is well behaved? So we'll have a brief tour. Okay. Okay, so this update rule, the joke is this. Okay, if you look at this update rule, okay, if you join a company and if you say you're doing TD learning or Q learning, I mean, your manager will probably surely recognize that. The way to get around is you say that I take Robbins-Monroe stochastic approximation. I'm implementing it. And say that I'm doing simulation-based value iteration. This is just simulation-based value iteration in the sense that you have a box which is probably a simulator. I don't think you try out things in reality. You don't go to the real world and try it out in practice very often. You probably build a simulator. So you take simulation-based value iteration. So what you're doing here is value iteration. So instead of throwing out popular, like RL is popular now, so don't use terms like TD learning, Q learning. Implement TD learning, Q learning, and say that you're doing simulation-based value iteration. The manager will be mighty impressed. Yeah, just throw jargon. This was what I learned when I was working. It worked reasonably well. I didn't get promoted, but I didn't get kicked out also. Yeah. So a brief tour. Yeah, there are some manager jokes that I can do, but not today. Yeah. Because there's just 1 hour, 1.5 hours left. So if I have f of x equals x by 2, this is when I start drawing. If I start at 32 and if I apply once, what do I get? What? 16, thanks. Then 8. 4, and so on. Finally, where will I get? Where will I get finally? 0, right? So limit as n goes to infinity, right? Is that clear? Clear? Start with any x, does not matter. It will keep shrinking it. Now what is f of 0? 0, okay. So what has just happened? If I keep applying f, it is like doing value iteration, okay. And then it converges to a point which is the fixed point, okay. But the reason why I call it a contraction mapping is because what is the function doing to your x? It is just shrinking it, okay. That's the contract part. It keeps on shrinking and you push it down to 0. 0 is, there's nothing sacrosanct about 0. You could take any other function. You can set the function as something else. If you want f of x, if you want a fixed point to be 2, you just have to adjust x by 2 plus something and you will get fixed point as 2. And eventually it will converge to that fixed point if I keep applying f. And that point it will converge to will be the fixed point, okay. F of x will be equal to x there, okay. And so the definition of a fixed point, not a fixed point, a contraction mapping. So if you have a contraction mapping, then it will have a fixed point, okay. All right, do you understand? If you have a contraction mapping, it will have a fixed point. The point I want to make is, all the operators that we have seen yesterday, t pi and t are contraction mappings, okay. And that's the reason why when I did value iteration, when I keep on applying it, it converts to the fixed point. Okay, I'm going to write out all these claims, but this is the point I'm trying to make. At the easiest level, at a very high level, I mean very simple, as a simple example, you have a scalar function like this, function of a scalar variable. And this is what happens even more generally. Okay, so the definition is a function, if you have a real valued function, is a contraction mapping with different people call this different thing, modulus beta, whatever. Some other people call it something else. Each time I apply the function, I'm going to shrink the distance. Beta is something which is strictly less than 1. Okay. Each time I apply the function, okay, I'm going to shrink it. Yeah. Okay. So beta is strictly between 0 and 1. It can't be 1. Okay. And that beta is why it is contracting. Okay. All right. Is this clear to everyone? Yeah. I mean, for that x by 2, the beta is just half. You're just cutting it by half. Yeah. So did everyone understand contraction mapping? So this is the crash course on contraction mapping. This is where it does not end, but we'll continue. Clear? Clear? Now we'll make the RL connection. Now MDP connection and then the RL part. What color? So I'm not going to recall these operators. Okay, this is a 6 credit course. Should have spent 16 hours yesterday night to understand what these are anyway, to revise this. Yeah. If it's a 6 credit course, how many hours is it? If it's 12, yeah? No, per week you have to spend some number, right? 6 hours. Yeah. Okay, so the point is this contraction here in the scale, or in this case, when I define the contraction, see the point is when you say something is contracting, you are saying that some distance is getting smaller. So you need some notion of a distance. Okay. So if you have a real valued function, the notion of distance is fairly, straightforward. You take the absolute value. That's already measuring the distance. But when you're talking about an operator like t, you need to say, when you say that it is a contraction mapping, you need to say under what norm it is. Norm is the thing that will say, okay, this is how I measure distance. Okay. So these are contraction mappings under what is called a sup norm or max norm, which is defined like this. So you have a n vector. You have a vector of n numbers. Take the maximum, that's your sup norm or max norm. Okay. And now that's a norm. If you don't know norm, then read the wiki page. Yeah, read the wiki page. You can't define it now. Now, if this is the way I measure distance using this norm, then I can show. It's not difficult to show, but I'm just going to claim. Now, the discount factor is something strictly between 0 and 1. And so that's the modulus of that operator. Do you see in that norm, when I apply t, okay, to a vector j, then I'm shrinking it. Okay, there should be a norm, and that norm is this. Okay, so it's a contraction mapping in a certain norm. Okay, got it? So this, even, I can write this for t pi also. Okay, one more equation. The same thing holds for t pi. Yeah? Any questions? Okay, so this is the first any questions. Any questions? Is everyone clear about this? Yeah? No questions? Now, if I apply this operator t once, I shrunk it by alpha. Okay. If I apply it again, if I do t square j minus t square j prime, then alpha square. If I do it k times, alpha power k. Okay. So once you have this fact, the other fact follows trivially. Okay. Okay. Now if I take j star, okay, if I set j prime equals j star, then how many ever times I apply t, what do I recover? J star, okay. So another corollary. So this is a corollary to corollary, okay. Yeah, and that's where it went. Another corollary. Now, this is a very interesting statement. What does this mean? If I start with J naught, okay, and if I apply the operator T k times, okay, and whatever I get here, what do I get here? This is like the after k steps of value iteration. After k steps of value iteration, whatever I have, if I measure the distance of that to the best, which is J star, then that has shrunk by this much when compared to whatever I started with. So this is an answer to one of the students who was asking a question yesterday. This is how quickly our value iteration converges. Okay. So put an alpha value. I mean, if you want definiteness, put k equals 50 and put alpha equals 0.9 and see it's already a very small number. Okay. Got it? See J naught. See, this is for all practical purposes, this is just a constant because you start with the J naught. If you fix that J naught, this is just a number. You're not changing that in the algorithm. Okay. And each time I do the update, I'm shrinking this number by an alpha, which is like 0.9, 0.8, whatever. Okay. So if I want this to be very, I mean, after, you can expect like after even 50 or 100 iterations that the output of value iteration should be very close to the J star. Okay. So that really is the expectation. So the point is this is like a convergence rate statement in the sense that each time I do value iteration, I'm getting alpha close. Very naively put. Yeah. Okay. Is this clear? So that's just a side benefit. But the important thing is all of this occurred simply because that operator T is well behaved, which is it's a contraction mapping. Okay. And that's what our H will be when I do incremental updates. Is this passage clear? Any doubts? So we'll have a stochastic iterative algorithm for finding fixed point of a contraction mapping. Okay, that's what we are trying to do. So the goal is solve HR star equals R star. So all this passage with the MDP detour is to show that you have a contraction mapping underlying a discounted MDP and you are trying to find the fixed point, I mean, of that contraction mapping that is well behaved. So I'm going to put it in an abstract framework now. HR star equals R star, where as before this is an operator. If you pass an n vector to this, then it will throw out another n vector. Okay. And now the update rule is like this. So I'm going to put it as ith coordinate because it makes job simple. So the point is there are n such coordinates. Each coordinate of R is updated like this. 1 minus, this is the step size. No, I can't use n. Plus beta t times okay, and this is the noise. So this is the dabba I was talking about. Okay, so you don't see H, you don't see HR, but what you see is HR plus W, where W is the noise. Okay. Now, when will such an update rule converge to R star? Okay, that's the question we want to answer. Throw in all the information you have, say R naught of I until RT of I and W naught of I to W T minus 1 of I equals 1 to N. Okay. And call this as, call this FT. This is all the information that you have up to time T. Okay, up to time T, all the information, all the iterates that you saw, all the noise values that you saw. Okay. Now, so this is the history. Okay, this is the history in more serious parlance. It's a sigma field, but we'll not get there. Now, the assumption that I want is the expectation of Wt of I given Ft should be 0. Okay, so the simplest case is when you know W is 0 mean. So the point is here, what I am trying to say is this Wt that I get is not even IID. It's not even IID. Whatever I get, it could depend on all that I have seen so far. Yeah, but it should conditionally be 0 mean and have conditionally a variance that grows like that. Okay, yeah. I mean, the simplest case that you can think is like, you know, it is IID, some normal 0, 1 each time or normal 0, 10, then it easily satisfies this. But what we are trying to say is in an RL setting, based on the entire information so far, you could have much richer noise structures. Okay, it's a richer noise structure and this is what you'll have to live with in an RL setting. The other standard assumption is this. This is the easiest bit. Okay. And the third thing is H is a max norm pseudo contraction. I call it a pseudo contraction because what I require is okay. I don't require full contraction. A full contraction would be something like this. And this is for all R comma R prime. Now what I am trying to say is when I say pseudo contraction, I only want this property with the second guy thrown in as R star. I don't care about the full contraction where I could have this property for R and R prime. Okay, yeah, it's enough if it works only in, you know, it's like contracting only with respect to R star. Okay, and now under A1 to A3, Rn converges to R star with probability 1 as goes to infinity. See, the very first assumption on W is like saying that it has 0 mean conditionally based on whatever history I have seen. Okay, it has conditionally 0 mean and bounded variance roughly. The second assumption is a standard step size assumption. The third one is the contraction mapping. If you have a contraction mapping, if the noise is not too much, that is A1, and if you have step sizes that follow some rules, then an update rule like whatever I had written before, then an update rule like this, RT will converge to R star. Okay. Yeah, I keep forgetting that R, I can't write Rn. N is the number of state. That's an unfortunate notation. Okay, so RT, yeah, RT would converge to R star. If an algorithm like that would converge to R star, if H is well behaved, which is a contraction, and if that W noise is zero mean and bounded variance, which is assumption A1, and if the step sizes are like 1 by T, okay, that's the most popular step size, okay, then RT will converge to R star, okay. And now we are ready to get into TD. So if people have got this, I'm not going to verify these assumptions for the two algorithms that I'm going to present, but I think it's not very difficult, okay, yeah. If I get time today, maybe, but not sure, yeah. Yeah, is everyone clear about this claim? Clear? Yeah? No, it can depend on RT. It's still okay. You don't want it to be like absolutely bounded above by some constant. We are saying that in more generally, if it grows linearly with RT also, it's okay. Yeah, so that's like a linear growth condition. It's like, it's okay. I mean, the point is, if you have a situation where it's just expectation of WT square given FT is just less than equal to some constant, that's already within here. Yeah, yeah. You just, I mean, so the condition should be read as there exists A and B such that that happens. Okay, A and B. Yeah, I don't have time for another intuitive justification for this algorithm because I have to do this and Q learning. What do I have to do? Or I can still do this intuitive justification because this is at the heart of this. Let's try this. Okay. I think Bertrand Russell said don't trust any proof by pictures. Okay. And this one of my instructors said, I didn't bother checking if Bertrand Russell said that. Maybe one of you can confirm later. So this is a proof by pictures. For definiteness, imagine h of 0 equals 0. Okay, you have some h. Okay. So r star equals 0. Okay. And imagine you start with an r naught that is at most like this. Okay. Yeah. And all you are doing is imagine there is no noise also. Okay. All right. Then what is happening is, imagine you have a box. You start with a box like this, so this is at most 2c wide. This is R naught, and each time you apply this, what happens is, I have to change the color. The box shrinks to 2 beta c. This would be R1. I mean, R naught was like at most, the norm was bounded by this. And then I apply H. Okay, and there is no noise. So each time I'm shrinking this box, by beta. And this box keeps shrinking and finally it goes to 0. Okay. Now the point is, this box shrinking is immediate if you don't have noise. Okay. Whereas if you throw in noise, what happens is this shrinking happens, but it takes a while. Each time for it to shrink, it takes a while because there is noise. There is zero mean noise with certain variance. So it takes a while for each time, I mean, for the iterate to get from this box to somewhere within this box and then to get inside this box. If there is no noise, if you have something like direct value iteration, the convergence is really quick simply because there's no noise, you just shrink each time, okay? You're entering smaller and smaller regions and that's the contraction idea. But if you have noise, you have similar behavior but at a slower rate. The slower rate is simply because there is noise, okay, slow rate, simply because you throw in the more general case, what you're doing is RT plus 1 of I equals 1 minus step size RT of I plus step size into HRT of I plus WT of I. Now what we are trying to say is, if you in the long run, if you want to see something like this shrinking behavior and going to zero, then this noise should not be too large. Okay, noise cannot be too large. If the noise is so large that it is not zero mean and it keeps hurting the algorithm and taking it nowhere, then that shrinkage won't happen. So the noise has to be well behaved, and the step sizes could not be arbitrary. They have to finally shrink. These step sizes have to be shrinking and finally go down to zero, but not very fast. The step size, see, for example, if after 2 iterations, if that eta t becomes zero, then the algorithm goes nowhere after that. Okay, the algorithm will be stuck wherever it is. Okay, so the step sizes have to go to zero, but not too fast. Okay, and those are the conditions for step sizes. Okay, so this is like a very intuitive. So the point is, you get similar behavior to that, but at a slower rate, simply because you have noise. Okay, and that's the reason why you have the step sizes in business like that. Okay, in this case, similar behavior, but shrinkage is not immediate. The reason I write this is because if you do one update in the previous case without noise, there's immediate shrinkage. Okay, whereas an update like that, the below one in red color, the update rule, the shrinkage is not immediate. You do one update and the R will not suddenly come and sit in a smaller region. The shrinkage is not immediate, but it will happen. Okay, that's really the idea. Okay, you can get on to temporal difference learning. Any questions about this passage? Anything? We'll be doing temporal difference learning next, which is the main takeaway. Yeah. Any questions? Surprisingly, no questions. Oh, I can't read faces. Temporal difference learning. So this is an algorithm only for policy evaluation. Okay. I hope you know what happens is you have fixed a policy. You have fixed a policy and you want to get its corresponding expected cost, J pi. Okay. And in Sutton's book, it's called the value function. Okay. It's one and the same thing. Okay. Value function or cost to go, there are many names. Yeah. So you fix a policy pi. Okay. And you want to estimate now I've made, see, the point is I could write pi of im each time, okay, but that's just unnecessary notation, simply because the pi is fixed throughout the discussion about temporal difference learning. So I'm going to skip the dependence on pi in the single stage cost function. Okay. Understood? The pi is fixed. You can rewrite all of that, this discussion, you can rewrite the whole thing, throw in a pi of im in between. Nothing changes. Okay. I'm just saying that the cost just depends on the current state and the next state. And we have fixed the actions. We have fixed the actions in the sense we are saying that we are taking actions according to pi. Okay. So we are not losing any generality in that sense. Okay. Now, what's the Bellman equation for this? Or the fixed point equation? That is J pi equals T pi J pi. Okay, that's something we saw yesterday, which is like, if I want to put it out, is expectation of, I'll call I bar as the next state, which is sampled from the distribution, plus alpha times J pi of I bar. And that the expectation is over I bar. Okay, all right. I mean, if you want to write it as, summation P I J, I just don't want to write that. Okay. I mean, does everyone understand the Bellman equation? Yeah? I bar is one of the next states and you're taking expectation over the next state. Is that clear? So the Bellman equation was exactly like this, or the fixed point equation. When I write T pi, I take an average over the next states, and for what am I averaging? I'm taking the G plus alpha times J of the next state. Okay? Yeah? And that's exactly the Bellman equation. I've just thrown in inside the expectation simply because I want to write this down as a fixed point iteration. Okay? So what I want to do is, now here you have the you have the operator staring at you. So the point is, the fixed point operator is T pi, okay, and that is doing this, okay. So if I want to write down an incremental update algorithm, the very first TD algorithm would do something like this. So this is called TD0, and I don't know if I'll be able to do TD lambda, but TD0 does this. So it maintains an, JT is your update, okay. It's your estimate of the value function. And using the previous thing, what I have to do is 1 minus eta t into the current JT, okay, plus eta t into, I ran out of space. Plus eta t into, what do I have to put here? I have to put T pi, okay. T pi involves an expectation, which I don't know, okay, yeah. So what I do is I just take a sample from that and write it down. I write it as G of I comma I bar plus alpha times Gt of I bar, where I bar is sampled from, okay. So this was the sampling thing that I was talking about yesterday. Somebody samples from that transition probability and says that, okay, this is one of the next states, just take it, okay. And using that, you write that. And now this is TD0, okay. Now I'll try to motivate why this is in that stochastic iterative algorithm that I was trying to write before, okay. But does everyone understand this algorithm itself? Yeah? So you are in, for example, you are in state I, okay, and you take action pi of I, and you see one of the next states, I bar, one of them, okay, okay. And then what you're doing is, you cannot write down that expectation, which is like applying T pi operator directly. But whatever goes inside that expectation, that part you're going to use to update your estimate. Is that understood? Yeah? Any questions? Now, why is this like, whatever I was saying before? So, I can rewrite this as, so, don't know why I wrote like this. Sorry. Wanted to write some other equation, I wrote this. Same as before, plus what I am going to write this eta t into okay plus I've just added and subtracted t pi jt of I. Okay. I've just added and subtracted t pi jt of I. Now I'm going to write this as jt of I okay. Now if you recognize what is the difference between this term and this term? What is the difference between this and this? I would write something like this, but throw in the summation pij's. That would go into t pi. Got it? Yeah? So you have a random variable minus its mean. Okay? Yeah? And if you throw in an expectation of this guy, then what you get is a zero mean thing. Okay? That's something you'll have to think about, or at least ask a question so that I can try explaining again. Okay. So that part is the noise. Okay. If this was not there, if this noise term was not there, then you are applying t pi again and again, except that you are smoothing with the step size, and you will converge to whatever I said. You will converge to the fixed point of t pi. That was the claim. If we want to go back up, if I want to show the stochastic iterative algorithm again, the update rule is like saying that without noise. I mean, so I want to put it as you have an n vector, you have this plus a contraction mapping sitting inside with or without noise. Okay, and this update will converge to the fixed point of the contraction mapping. Okay, so that was what was happening. And so if I come to TD, that's exactly what I am doing. Okay, so this is my noise bit. This is my noise bit, and this is the bit which is the contraction mapping that I care about. So this algorithm JT would converge to, some J star or J pi. This JT would converge to J pi, okay, which is the fixed point of T pi. Okay, that's really the assumption. You will have to go back and verify all the conditions on WT, but the motivation I'm trying to do is you have a sample from a random variable. Okay, now if I want to explain this even better, you can connect this to mean estimation. What do you want to do? You want to estimate the mean. Okay, this is like expectation of something. Okay, imagine you put all that something as some random variable. You want to find the expectation of this. Okay, what am I doing? I'm taking a sample. I'm taking one sample. Okay, I'm doing my update. So when I started today, if you had paid attention, if you go back to the very first mean estimation that I did, look at the update rule and you will know what I'm talking about. So what is this boxed update rule doing? I want to estimate expectation of V. Mu is expectation of V, okay? And I'm taking a sample, okay? And I'm doing this update, okay? And so this is like 1 minus 1 by n plus 1 into Rn, all right? Plus 1 by n plus 1 into Vn plus 1, right? Understood? So what am I doing? Effectively the same thing. I have the expectation of some random variable that I want to estimate, and I'm taking a sample of that and making that update. So instead of step size, you can put a step size, you do 1 minus step size into this Rn plus 1 by step size, plus step size into the sample that you take, which is exactly what I'm doing now, okay? If you come down to this update rule for TD, it's exactly what I'm doing here. If you look at the update rule, I want to estimate this expectation, okay? I do 1 minus step size into JT plus step size into a sample, okay? This is a sample of that, okay, whatever goes inside. I'm just taking one of the samples. I take a sample and I update my algorithm. And that sample can be written as sample minus its expected value plus expected value, okay? And that sample minus its expected value is a zero mean quantity, okay? If you take a random sample, okay, and subtract its mean and then take the expectation of that quantity, what is that? That can only be zero mean. Was this clear? Clear now? So that's exactly the WT I'm talking about. This is a sample from this, okay, and this guy is like an expectation of something. So if you take a sample minus its expectation, and if you take expectation of WT, then that is zero mean. I mean, it has zero, yeah, mean. Simply because you are subtracting the mean. If you take any random sample and subtract the mean, then you are almost like, yeah. Yeah, that's the most I can explain. If anyone has a question, let me know. Any questions? Any questions about this learning idea really? No? Is everyone clear about TD0 algorithm? Now the point is, what I'm not going to talk about is here, instead of taking this expectation, which is like you take one step in the MDP, okay? You take one step and then approximate the future, okay? Instead of that, I could do G of I comma I bar plus alpha times G of I bar comma I double bar. So I sample the next state and then one more state after that. And then plus alpha square into J pi of I double bar. I could do that. And I can write down an update rule, okay? And I'll get another TD algorithm, right? I do 2 steps and then approximate the future. I could do 3 steps and then approximate the future. I could do, any number of finite number of steps and then approximate the future. Okay, each of them will give me an algorithm. And there's a way to approximate, combine all of these into one algorithm. That's the TD lambda algorithm. Okay, and that, requires a lot of work to actually show how that works. I'm not sure if I'll be able to cover that. So I'll actually move on to we'll probably move on to Q learning simply because it's pretty involved to teach TD lambda. The other thing I want to say is effectively please recognize what am I doing in the here. I have a learning setting, but effectively what is the type of this algorithm? It is a value iteration algorithm. Simply because effectively I'm trying to apply TPy again and again. I've thrown in noise so that it's a little slow because of the noise, but eventually I'm getting to wherever the value iteration was getting to. Okay, yeah, is this clear? Is TD algorithm clear to everyone? And the reason why it is called a temporal difference is because where is the update rule? The reason why it is called a temporal difference is simply because of this. Okay, this is the reason why I was trying to write this algorithm again. Okay, It's the same thing. I've rewritten the same update rule. It's instead of writing 1 minus eta times gt, I've brought it inside on the right side. And whatever is here, this part is the temporal difference. That's my best attempt at explaining temporal difference actually. Yeah. Simply because, you know, see when I say jt of I, this is your estimate of the value function or the cost, okay, starting from the current state, okay. And then what you do is you take one step and then approximate the value at the next state. And so this difference is like a temporal difference, yeah. That's a nice enough name, yeah. I should learn to make up nice names like that instead of saying simulation-based value iteration, you know, yeah. But you should have a name that only you know, so that your manager does not know, yeah. I made up a new algorithm, yeah, some Samba algorithm or something like that. I wrote a paper with salsa algorithm, it got rejected. Then I changed the name, yeah, something. And people are not into paper writing, so these jokes don't sell well. So we'll get into Q learning. This is the last stop. Any questions, remaining questions? Nothing? Yeah, either it's profound silence or nobody got it. Sorry? No, actually, stochastic algorithm for least squares approximation. That was salsa. Submitted it to AAA. It got rejected. Then I made it RORSA, ROARSA. And then RORLASA. I tried all combinations. And then I got rid of all of them. And then wrote something very, very bland. Yeah, I can't remember that. Yeah. It was a long while ago. But I have an algorithm which is called woeful. It's got published. Yeah. Weighted optimism in the face of uncertainty linear bandit algorithm. Yeah, so if you are into bandits, you know this optimism in the face of uncertainty. And there's a linear bandit. So there was an woeful algorithm. Okay, and I made it, I throw in the weighted part to make it woeful. Yeah, my experiments in, yeah. And I tried to write a paper title which was like inspired by some Kubrick movie. How many of you have heard of Stanley Kubrick? Yeah, I expect that. Okay, which is Stanley Kubrick's best movie? Oh, I slept through that, yeah. I didn't get it, I don't know why. How many of you seen this 1952 or 53 movie, The Killing? It's almost like a Tarantino movie. Be shocked, yeah. It's a black and white movie, it's about a heist and how many of you are Tarantino fans here? How many of you are Nolan fans? In my class, usually the Nolan fans outnumber. Yeah, but I'm not a Nolan fan, yeah. Yeah, but anyway, there's one Nolan movie which I like, yeah. Which is the best Nolan movie? Huh? Prestige, somebody said that? Yeah, seriously, I also think the same way. All his Batman movies are like Rajnikant movies for me. Yeah, better effects maybe, but what else? I mean, okay. Especially the last one, you know, carrying something in a helicopter and almost Sunny Deol-esque. Yeah. Yeah, things like that. I mean, they caught our patterns much later, like Titanic and all that. We had been doing this formula, but I mean, we do it in almost every movie. They do it once in a while. So their movies stand out because, yeah, there are many other for, yeah. Anyway, move about movies some other time, yeah. So what we looked at previously was policy evaluation, okay. Policy evaluation is like you fix a policy, try to find the best. We'll try to do control now. which is trying to find the best policy. Yeah, trying to find the best policy. So instead of t pi, you have the operator t, and that lends to a few difficulties which is very hard to explain, but let me try. So what you do is let J star is the optimal cost. Okay, yeah. And then you define what is called a Q star. Okay, Q star is summation or J. Okay. Okay. What I have done is, if you look at, so the point is here, when you say J star, you are saying that I want to try to find the best path in starting in a particular state. Whereas here, what I am trying, so what you do is you fix the initial state in J star, you fix the initial state and you want to find the optimum sequence. Okay. Whereas in Q, what you do is you fix the initial state and also the initial action. Okay, that is A. So which is like saying that I take one step in the MDP using action A, and after that I want to be optimal, and that's the Q star. Okay, I call it Q star, and there's a connection. There's a connection in the following sense. Now the point is I'm trying to build this up so that I come up with an algorithm where I write down some expectation and then I sample from that and I get the algorithm. Okay, so this build-up is exactly like the TD build-up in the sense that I want to get to a point where I have an expectation of something, okay, and whatever that something is a contraction. I mean that expectation of something is a contraction mapping, okay, and that whatever is inside I can sample from, and I'll use that sample to do the update, okay. Yeah, when you look at J star, you don't have that luxury simply because J star is minimum of something. See, if it's minimum of something, the expectation comes afterwards. Minimum of summation Pij whatever. Okay, so I cannot take a sample and write a minimum and write an update rule. Do you recognize this? Okay, so what I want is, I want expectation of something. That's the reason why I fix the first action. I fix the first action, so there won't be any minimum in the current state, but there will be a minimum in the future states. That's exactly what I'm trying to get to. Okay, so I can write a Bellman equation like this. Bellman equation says J star is minimum over A summation j equals 1 to n Pij of A into G of Ia j plus J star of J alpha. Okay, if I forget an alpha, just remind me. Okay. Now whatever inside that, whatever this RHS, this summation I have defined as Q star. Okay, that's by definition Q star. Do people recognize that? Yeah, so I can write J star of I is minimum over A Q star of I comma A. Sorry? Huh. Oh, this is alpha. Actually, I ran out of space. I just tried to squeeze the alpha there. Some stupid thing. Actually, I'll try my best to squeeze an alpha here. Yeah. So, that's the alpha. Actually, yeah, but okay, so this passage should be fairly straightforward. See, in the Bellman equation, whatever goes after the minimum, I've defined it as a Q value. Okay, so that's a Q value. When I say Q, see when I say J value is for a particular state. Q value, you fix the action also in addition to the state. So this is the Q value for state I and action A. Okay, this is the Q value, and the way to relate J star and Q star is take Q star and add the minimum, you get J star. So Q star, what it does is, in state I, it takes action A and then does the optimum thing afterwards. Whereas J star has to do optimum thing right from step 1. So you have to minimize over A in Q star. That's all there is to it. Okay. But this Q star is more amenable for an incremental algorithm, and that's where we'll try to get to. Okay. So I can write a Q Bellman equation. This is normal J Bellman equation. The Q-Bellman equation. You will not find it in any textbook, okay? I mean, you'll find the Bellman equation, but they won't call it Q-Bellman equation. Not like why? Why do you need this Bellman equation? Q, like that. Now alpha times C, I want a Bellman equation where I need Q on both sides. Okay, I want a Q here, I want a Q here. Okay, but what I got there is I got J star there, right? I got J star, but there's a way to go from J star to Q star. Understood? Okay, so instead of writing alpha times J star, I can write minimum over A, J star of next, I'll write it. Q star of this. Okay, I want to write J star of J, I'll write it as minimum over something. But this is not minimum over A, but this is minimum over B, which is the actions of the next state. Q star of, I ran out of space. Okay, I think I can squeeze something. Here. Okay, so this is a Bellman equation. Okay, so this is a Bellman equation and it's like a fixed point equation. You want to do Q of something, you apply this operator, and you have to recover Q. Okay, if you apply this operator to Q star, you want to recover Q, which is like what you are doing in J star also. You take J star, you apply an operator, you recover J star. Okay, that's like, oh no marriage jokes, yeah. Okay, so the point is this, again you can show that this, if I replace this whole RHS by some operator playing on a Q, that operator is a contraction mapping, okay, for reasons similar to previous case, okay. So what I got is a contraction mapping, but the important thing is, this is like summation Pij of something, right? This is like taking expectation of this quantity, okay. If you see above, there was a minimum and then there was an expectation. In J star case, you have minimum and then an expectation, whereas when you talk about Q star, since you are taking any action here and not the best action, the minimum went inside, okay, yeah. And this was like the one-line thing that my PhD advisor told when I joined for a PhD. I asked him, what is Q learning? He told, took me 1 year to get here, yeah. But you people have got here faster, hopefully, because of 3 lectures, yeah, from a benevolent instructor, yeah. So now I just have to make up an algorithm like this. So this is like expectation of Giaj plus minimum over P Q star of J comma B. Where again, as before, J is sampled from. Okay, there's no policy here. You're fixing the action. So you fix an action, okay, and you sample a next state, and you write this down, and then you want to recover Q star here. So this is the Bellman equation. I should try shading in another color. I think it's what. Yeah, this is modern art. Now how do I turn this into an algorithm? I just write down an incremental algorithm. Instead of this expectation, I just take a sample from this, and I got the algorithm. And what is that algorithm called? What is it called? Q learning. Like if you are from North India, why do you want to learn? Yeah. और क्योंकि learning भी कभी something था, क्योंकि professor भी कभी student था, or something like that. You can make a soap serial of this. Yeah. I don't know. I have a serial joke, but that you have to come to my ML class. So the update algorithm, the Q-learning algorithm, let's write it down. Okay, I'll write it like this simply because I want to show some, this is also like a temporal difference business, okay. So g of I comma a comma I bar, I don't know why I switched to I bar, okay, minimum or b, qt of I bar comma b minus qt of I comma a, and that's all there is to Q-learning. Okay, I'll just define the operator and probably in like 5 or 10 minutes we'll be done with this. Yeah, done with this introduction. Yeah. Any questions? Actually, yesterday there were more questions. Today people are not willing to ask. Either things are super clear or, oh, I told this already. Yeah. Okay, so you just want to figure what is the operator underlying this. So you can define the operator. Okay. So you take a Q and apply the operator H. Now you are applying it for not for a state but for a state and action tuple. Okay, both state and action are there, and then you have a Q. Then what you do is summation j equals 1 to n p I j of a to g of I a j plus minimum or p q of j comma p. Actually, for simplicity, I'll just make this j. Don't want to change things. J. Okay. Yeah, that j is sampled from the transition dynamics. Okay, so that's the operator. Okay, this operator H is again a contraction mapping, so norm, pseudo contraction. Okay, yeah, this operator H, and then you can verify all the conditions that I had put out a while ago. Okay, I had 3 assumptions. If you remember, I had 3 assumptions. The first assumption was you required a contraction mapping to be sitting underlying this update rule. The second assumption is obviously the step size assumption, that is automatic. You don't need to do any work to satisfy a step size conditions. You can just set the step size a certain way easily. And the last thing is the noise. And so the Q-learning update rule can be written okay, so that's where the noise came in, where Wt of I comma a is g of I a. Oh, now this is why I need I bar. Very sorry about this. It's easier to write I bar. So g of I bar. So this is the update rule. So plus alpha times minimum. Oh, there is a alpha here. I don't have space to put an alpha. Will nobody notice the alpha? Missing alpha? Okay, that's a minimum. I'm tired of changes. In fact, to make it more clear, I'll just write down the whole HQT so that you know, understand what is the difference. Summation now you see the difference. So the point is, this WT is just, you take sample from this. Instead of J, what you have is just one random sample, random next state, okay, sampled from this distribution. And then that difference turns out to be the WT, which is zero mean, okay. And the update rule can be written like that, and that goes back to the stochastic iterative algorithm, okay. And if you believe it's easy to work out that H is a contraction mapping, you can check Batsika's book. Or take my RL course at some point in the future. So you will see that H is a contraction mapping. It's very easy to bound. It's fairly straightforward to show that W is conditional zero mean. Showing that its variance is bounded is also very simple. Assuming if you assume the costs are bounded, the state space is finite, the actions are finite, then it's easy to show that WT square, an expectation is bounded. Okay, so it can be shown that A1 to A3 listed earlier hold for not this star and okay, yeah, Qt converges to Q star almost surely as t goes to infinity. The important point is, if I have Q star, I know how to act optimally. Okay, given any state, if you go back to the definition of Q star, if I am given Q star, then what is the optimal policy? In a particular state, what is the action that I have to take? The one that minimizes Q star, okay? That's the optimal policy. That's the side benefit. If you have J star, you have to work back and get something like Q star. But in these algorithms, you directly get Q star, okay? But that was not the motivation. The motivation was this expectation and minimization business. And but this Q learning will converge to something like Q star. And once you get Q star, you know how to play. I mean, you know which is the best action to take, and that's the optimal policy. Okay, so Q star is what you want in a MDP, and that gives you the optimal policy. What I've really sidestepped is, see, for example, if this, I mean, if you want to take, if you want this algorithm to do well, there's something called an issue of exploration, which I'm not discussing. I'm going to end very soon. So the point is, this update rule, so this is like a table. Q is like a table, one entry for each state action pair, okay? And you're going to update each entry. Now the point is, each entry, the quality of that entry will be, how good it is will be based on how many updates I carried out on that. So when you update, if you just see half a dozen state action pairs, okay, and then if you update only them, then only there you have learned something, okay. Whereas if you want Q star should be like for all state action pairs I need Q star. So when you update, you should, explore so that you update all the state action pairs. Okay, you visit all of them many times so that the Q tables have good enough values. Okay, that's the issue of exploration. You cannot, just focus on just 10 states and try some actions there, because that won't give you the optimal policy in all states. Okay, and that can be forced in many ways. You can do better exploration